Here in this section we have improper integrals. Definition: integrals with infinite limits of integration are improper integrals of type 1. Number 1, if f of x is continuous on a positive infinite, then integral a to positive infinite f of x dx is equal to limit as b approaches positive infinite integral a to b f of x dx. So here we have bracket and that is closed. Number 2, if f of x is continuous on negative infinite comma b, here we have bracket, it's closed, then integral from negative infinite to b f of x dx is equal to limit as a approaches negative infinite integral a to b f of x dx. Number 3, if f of x is continuous on negative infinite comma positive infinite, then integral from negative infinite to positive infinite f of x dx is equal to, so here we have two parts. The first one, integral negative infinite to c f of x dx plus integral from c to positive infinite f of x dx. C is any real number. In each case, if the limit exists and is finite, we say that the improper integral converges and that the limit is value of the improper integral. If the limit fails to exist, the improper integral diverges. Here on this part we have definition for improper integrals of type 2. The definition: integrals of functions that become infinite at a point within the interval of integration are improper integrals of type 2. Number 1, if f of x is continuous on, here we have parentheses a comma b bracket and discontinuous at a, then integral from a to b f of x dx is equal to limit as c approaches a from right integral from c to b f of x dx. Number 2, if f of x is continuous on, here we have brackets, so that is closed, a comma b, this part is open, and we have parentheses, and discontinuous at b. So we had parentheses on this part, that's why here we have discontinuous at b. Then integral from a to b f of x dx is equal to limit as c approaches b from left, integral from a to c f of x dx. Number 3, if f of x is discontinuous at c, where c is between a, b, and continuous on bracket a comma c parentheses union parentheses c comma b bracket, then integral from a to b f of x dx, that is equal to sum of these two integrals. We have integral a to c f of x dx plus integral c to b f of x dx. In each case, if the limit exists and is finite, we say the improper integral converges and that the limit is the value of the improper integral. If limit does not exist, the integral diverges. Theorem 2, direct comparison test. Let f and g be continuous on bracket a comma positive infinite with f of x between 0 and g of x inclusive for all x greater than or equal to a. Then number 1, if integral from a to positive infinite g of x dx converges, then integral from a to positive infinite f of x dx also converges. Number 2, if integral from a to positive infinite f of x dx diverges, then integral from a to positive infinite g of x dx also diverges. Theorem 3, limit comparison test. If the positive functions f and g are continuous on bracket a comma positive infinite, and if limit of f of x divided by g of x as x approaches positive infinite is equal to L is between 0 and positive infinite, then integral from a to positive infinite f of x dx and integral from a to positive infinite g of x dx both converge or both diverge. So example 1, the integral in this exercise converges. By this integral, we have integral from 0 to 13 dx over square root of 169 minus x squared. Recall if f of x is continuous on bracket a comma b parentheses and discontinuous at b, so here we have parentheses, that means it's discontinuous at b, then integral from a to b f of x dx is equal to limit as c approaches b from left, integral a to b f of x dx. So what we have here for this part, integral from 0 to 13 dx over square root of 169 minus x squared, that is equal to limit as c approaches 13 from left, integral 0 to c dx over 169 minus x squared, that is inside square root in denominator. So this is equal to, so we have to integrate, this is equal to limit as c approaches 13 from left. Integrate this part, we have inverse sine x over 13. So here we have square root of x squared. So here we have x squared. So on top, on this part, we have square root of x squared, and that is x. In denominator, we have, based on what we have here, in denominator, we have square root of 169, and that is 13. So we have x over 13, and this is from 0 to c. The next step, substitute limit of integration. So here instead of x, first use c. We have limit as c approaches 13 from left, inverse sine c divided by 13 minus, then use 0 instead of x, so minus inverse sine 0 divided by 13. And this is equal to, so what we have here is c approaches 13 from left. If we use 13 here, we're going to have 13 over 13 is equal to 1. So inverse sine 1, that is pi over 2, or in other words, sine pi over 2 is equal to 1. So this is pi over 2 minus, now here on this part we have inverse sine 0, and that is 0, because what we have for sine 0 is equal to 0. So here we have pi over 2 minus 0, the answer is pi over 2. So our final answer is pi over 2. So here on this part, the integral converges, evaluate the integral from negative infinite to positive infinite to x dx divided by x squared plus 1 cube. Recall if f of x is continuous on negative infinite, positive infinite, then integral from negative infinite to positive infinite f of x dx is equal to integral from negative infinite to c f of x dx plus integral from c to positive infinite f of x dx. C is any real number. Now apply this formula to the given integral for c equal to 0. So what we have here, integral negative infinite to positive infinite to x dx divided by x squared plus 1 cube, that is equal to integral negative infinite to 0 to x dx divided by x squared plus 1 cube plus integral from 0 to positive infinite to x dx divided by x squared plus 1 cube. So here instead of c we used 0. Now let u equal to x squared plus 1. This is what we have here in denominator. So that equal to u, and then derivative du is equal to 2x dx, and the limit 0 for the variable x becomes, so using x equal to 0 here on this part, we have 0 squared plus 1, so that is equal to 1 for u, for the variable u. Now integrate what we have here, integral from negative infinite to 0 to x dx divided by x squared plus 1 cube plus integral 0 to positive infinite to x dx divided by x squared plus 1 cube, that is equal to, so instead of x squared plus 1, we have u, and 2x dx, that is equal to du. So we have integral infinite to 1, so we had u equal to 1. And what we had for u, that was x squared plus 1. If we use negative infinite instead of x, we're going to have negative infinite square plus 1, so that is positive infinite. That's why here I have positive infinite. And then so we have 2x dx, that is in du, and here this part is u power 3. Move that one to the numerator. We're gonna change our power from positive to negative, so that's how we have u to the negative power, negative 3, plus integral 1 to positive infinite. Again, we have u to the negative 3, that is power multiplied by du, that is 2x dx. So 2x dx is du again. And this is equal to limit as b approaches positive infinite. So integrate. We have at 1, we have negative 3 plus 1 is negative 2 divided by same number, divided by negative 2. And then plus limit as c approaches positive infinite. Again, we have negative 3 plus 1, it's negative 2 divided by same number, negative 2. So for this part, we have from b to 1, and here we have from 1 to c. The limit as b approaches infinite using 1 instead of u. So we have 1 over negative 2 minus using b instead of u. We have b negative 2 is power divided by negative 2. So here we have subtraction. And then on this part, using c first instead of u, and then use 1 instead of u. So we have limit as c approaches infinite. C negative 2 is power divided by negative 2 minus 1 over negative 2. So the answer that we have here, we have 1 over negative 2 minus, instead of b using positive infinite. Here power is negative 2, so move that to denominator. We're going to have 1 over infinite. 1 divided by infinite is equal to 0. And then on this part, again, c approaches to infinite. We have infinite, power is negative. Because of having negative power, if we move that to denominator, we will have positive power. So that means we're going to have 1 over infinite. So 1 over infinite is equal to 0. And then minus 1 over negative 2. So what we have here is negative 1 over 2 plus 1 over 2. That is equal to 0. So this is final answer for this part.